Hello everyone, myself Dr. Harishankar Singh. In this video, I will give the details of electric field lines and electric flux. Here is the outline. First, I will discuss electric field lines and then electric flux. Let's start. As you have already seen in the previous video that the electric field intensity, that is E, is the force that a unit positive charge experiences when placed in an electric field. So, the electric field lines are nothing but a pictorial representation of the electric fields. These lines are indicating direction of electric field at any point in the space. There is no specific rule to show how many lines are to be shown in the pictorial view. However, it is customary to draw number of lines proportional to the charge. Thus, if n number of lines are drawn from or onto a charge q, then 2n number of lines would be drawn for charge 2q. The relative closeness of lines gives idea about the intensity of electric field. Nearer to the source, electric field lines are dense and become sparse as one moves away from the source. Electric field lines originated from a positive charge and terminated either on negative charge or moved to infinitive. These electric field lines never crossed to each other. If they did, the field at a point of crossing will not be uniquely defined. As I told you, an electric field lines are an imaginary line or curve drawn. Electric field lines always points away from a positive charge and towards a negative charge. As you see from the figure, in the first figure, from the positive charge, the electric field lines are in the outward direction, whereas if the charge is negative, the electric field line are in inward direction. If positive and negative both charges are placed close to each other, then electric field line originate from the positive charge and terminate at negative charge. Therefore, some conclusion can be made out for the electric field lines. The electric field line originates from a positive charge and terminate either on negative charge or move to infinity. Electric field lines never cross to each other. Closer the electric field lines, stronger is the field. The number of field lines depend on the charge, that is, bigger the charge, the more electric field lines. The direction of electric field E at a point is always tangent to the field lines. Now let's understand about the electric flux. Electric flux is the rate of flow of electric field through a given area, that is, the number of electric field lines going through a virtual surface. The concept of flux is taken from flow of the water through a surface. In this, the amount of water flowing through a surface depends on the velocity of water, the area of the surface, and the orientation of the surface with respect to direction of the velocity of water. Similarly, the electric flux through a surface depends on the electric field lines, area of surface, and orientation of surface to the direction of electric field lines. As we know, an area is generally considered as a scalar, but an element of area is a vector because it has both magnitude as well as direction. In general, an element of area is infinitesimally small and it is considered to be in a plane. Then we can associate a direction with it. For instance, if the area element lies in the xy plane, it can be considered to be directed along the z direction. Conventionally, the direction of area is taken to be along the outward normal. Therefore, in simple words, electric flux is the amount of electric field going through a surface. It is defined in the terms of a direction, unit vector, and perpendicular to the surface. Differential flux is defined as E dot n cap ds, where n cap is the unit vector which is normal to the surface. And in this figure you can see the electric field lines are making angle theta with the surface ds. So we can write differential flux d psi is equal to magnitude of electric field cos theta ds. E cos theta is basically number of electric field lines which will be crossing to surface ds. For an arbitrary surface S, the flux is obtained by integrating over all the surface element. So, from the differential flux d psi, we can obtain psi. Psi can be written as surface integral d psi, and it will be equal to surface integral electric field dot n cap ds. If the electric field is uniform, the angle theta is constant, then we have flux psi is equal to S E cos theta. E cos theta is basically magnitude of electric field crossing to the surface S. Thus, the flux is equal to the product of magnitude of electric field and the projection of area perpendicular to the field. When the surface is flat and the field are constant, you can just use the multiplication and get the flux. Multiplication of surface and the electric field lines. From the figure, you can see in the first case, the electric field lines are crossing to given surface. So in that case, theta will be 0. So flux psi is defined as Es cos 0. Cos 0 will be 1. We will get flux as electric field multiplied by S. But in the second case, surface is parallel to the electric field. That means there are no any electric field lines are passing through the surface. In that case, the theta will be 90. So flux psi can be written as Es cos 90. Cos 90 will be 0. So we will get 0 flux. So in the first case, what amount of electric field passing through the surface, just simply multiply the electric field with the given surface, we will get the flux. But in the second case, there are no any electric field line are passing through the surface, we will not get any flux. That means flux will be 0. When the surface is curved or the field are not constant, that means not uniform, then we have to perform the integration there. In that case, we can calculate the electric flux as psi is equal to surface integral E dot n cap ds. That means how much number of electric field line passes through the given surface S. Thank you for watching this video.